to a .java file source-wise. We're going to focus primarily on the first technique because that's the most interesting. Now, the problem with the technique, it's not an exact science, except in a few cases. And it's very difficult when you're looking at some code to actually ask the team that wrote or built the code for special artifacts. You know, create me a debug build. If you're building a full device, again on Android, you don't control all the steps of the builds. You may have a top-level makefile, but there's a build loop, and maybe you have no way to actually go and change all the makefiles to enable debug symbols in the right spot. That's difficult. The thing also, if you think about all the static analysis, you may be eventually able to conclude that a file is effectively built, but you don't know what's not been built. And that's also a problem. The last thing is, whether it's built doesn't mean it's effectively deployed. A common case in Go, for instance, is to have test files side by side with the main code in the same directory. All the code during a regular build will eventually be built, but your resulting executable won't contain typically the test code. Okay, so what would be the ideal solution? You want to have 20/20 in sight. It's like the God's invisible hand that's able to tell you exactly what happened during your build without doing any build modification, and have something that would be very accurate. And so the technique is to use something called syscall, or system calls. If you're not familiar with it, that's the language of the kernel. So the Linux kernel doesn't know about what's happening and nice web stuff you do in user space. It really knows about a very few simple operations. You can think of it as the assembly language of the kernel. It's machine language. It knows about reading files, writing files, opening sockets, doing network interactions, and a few other stuff, but they're very low level. Now, everything that happens when you do something in user space ends up in a syscall, one of these. And so the tool I'm presenting today is called tracecode. And what it does is using another tool called strace, which is a system call tracer, and you just run your unmodified build under strace. It captures every single system call that happens at the kernel level, so very low-level operations, read, write, open file, close file, that kind of things, on all the processes. And then it's parsing this trace and just rebuilding a graph of all these file transformation and all the executables that were involved in that process. And eventually, you can query this graph and understand exactly what are the source files that were used to end up in a build. It doesn't care about what you build. It could be tomatoes, JavaScript, C, C++, Java. It doesn't know. It only really reverse engineers the system call set, which is eventually messy and quite chatty, into something which is a set of file transformation done by a certain tool. So it's agnostic, doesn't know about the tool chain. It doesn't require anything to change. You just need to install strace and tracecode and run your build, prefix with strace and a few command line magic invocations, which are documented. You could run cmake, gcc, gmake, doesn't really matter. So quick presentation now, what it looks like, what you get at the end of it. So let's look at an example. Let me make it a bit smaller. That's a very simple build graph. There's ways to actually create a graph.graph at the end if you want, of a single file executable elf. It's called patch elf. It's a tool produced by the Nix distro for patching elf. And you can see that even building a single file is actually going through many steps. So if we look at the top, you have a bunch of housekeeping things. You know, there's some weird temporary files which are created. Make is looking at mail files, creating some PO files. But these end up like in dead branches of the build. And then here we see something a bit more interesting. You have GCC that's being called. And below here, what you can see is a bunch of source file. Well, you have elf.h in patchelf, patchelf.cc proper. And then, well, actually all the standard includes that were eventually used and included at some level by this C and H file. It goes into a second executable called cc1+, which is actually the GCC C++ preprocessor. This processor actually creates now .s, which is an assembly language file, so it transformed the C code in assembly code, created some other temporary file here to track dependencies. It's moving the file here in one place, invoking AS, which is the assembler, which transforms the assembler in machine code. Then eventually it creates a .o that's a relocatable elf object. And there's other branch of the build that end up dead instead in terms of they're not producing any more files on the top. And on the bottom, we finally invoke something called LD, which is a linker. It's going to take the .o file and create a real elf file. And you have patch elf. Now, I can query the graph and go backwards, and it's going to tell me exactly, these are the files that were used. That's pretty simple for a single file executable. It could be a bit more involved if you look at something like building cups, which is a tool that's used for printing on Linux. Eventually, it reached a point where building a graph for visualization is difficult, and you could eventually put that in the graph database and do partial queries. But the thing is that it's just data, so it can be queried. So let's look a bit at what it looks like in more details. It's even taxing a bit my very fast laptop to actually render this kind of PDFs. I'm zooming, and it's still syncing. Well, we'll leave it like that. All the test files, all these samples are available online, both in the project and in the FOSDEM webpage for this talk. So, step by step, what does it require to do? You need to install a trace, usually a recent version. You run your build under a trace, and can be anything, can be a large build or a small build. I've been tracing full stack Android builds. It's very involved. Makes the build about 2 to 10 times slower when you run it under a trace, because it captures a huge trace, which is in the range of 20 gigabytes of 400,000 files of processed traces. And then you install and run trace code on that trace. And then from that point on, you can build graphs, query, focus the query on specific parts. OK, now let's look a bit at other techniques. So we talked about debug symbols, build logs. One very promising technique in terms of static analysis is the following. Say you have a bunch of source code for a package and a bunch of binaries, eventually built for multiple architecture. So you take raw builds from Fedora and Debian for MIPS, ARM, x86, and you have the source code. Or you have a minified JavaScript and its corresponding source code. What you do is that locally, indexing step, you find the shared strings. You don't do any kind of processing on these. Just find what is the shared strings that exist, both wide and narrow strings, in this bunch of binaries and this bunch of source. What you get out of this step is the things which are eventually symbols, literals, name of structures, and so on, that will end up being built into whatever the binary is. The second step, you put that in an index, and then you take some arbitrary binary and trying to find, is there any of these strings that show up? And eventually you can rank it based on the number of strings that show in the binary. I was able to play, for instance, with Android applications and iOS applications to to discover that they were using a certain version of OpenSSL, a certain version of libpng, and zlib, even though there was no indication otherwise that could clearly show it. And eventually pinpoint pretty accurately which version, which is not a small feat. The thing, because every version will have slightly different strings, at the minimum, usually version strings, you can eventually get a pretty decent ranking and go to a mode where you could find the presence of arbitrary pre-built binary in a binary, even though you don't have access to the source code. And that's something I'll be working next. So, some credits. strace, of course, it rocks. It's a very old project. It predates Linux, if you don't know it. It's very active, and it's really the Swiss Army knife of any kind of hardcore debugging information. What I'm doing in scan code, in trace code here, it's not new. It's actually the implementation of a paper that was published by a certain Sander Vanderberg and Armin ML, that some of you may know. These guys are actually the guys that are behind a Linux distro called Nix, and a derivative of Nix called Guix. So trace code is available on GitHub. It's written in Python, it's Apache license, and quick plug about a few other tools I'm working with. And I built one's called Scan Code, is a tool for license detection. About Code Manager is a GUI to review scans for license, copyright, and origin. And Attribute Code is a way to collect and document information about the origin license of your code and eventually generate inventories and attribution notice. That's it. Questions? Oh, no questions? No questions? No? Okay.
Oh, I'll have a question if no one else has a question. Yeah, question down here.
Go ahead.
Sure.
Okay, thanks. Interesting talk. Towards the end, when you were talking about doing basically the string matching in arbitrary binaries and things like that. Now, is that part of any either available open source project today or proprietary product of yours, or is it still under investigation, development, research sorts of things?
That's something I want to release as an open source. I've just made a few local tests. So everything I do is released as open source except for the one commercial product that Nextbee sells. But all the tools for scanning, matching code, tracing code, we release everything as open source. The business we're in is to sell data, essentially. Data about open source code. So the tools are free. The data is eventually available with a subscription.
Thank you. Third question? Yeah.
So it seems like this technique is useful for like file level license compliance, but given the fact that you have package level visibility to the licenses, what's the advantage here other than being able to separate out test code in a third-party dependency versus what you would package when you actually link?
Well, take a practical example. So let's assume first that we all use linking as a proxy for derivative code and combined work under the GPL or LGPL. Linking in any case for the GPL and dynamic linking in the case of, well, static linking in the case of LGPL. You have a large number of Linux libraries. Usually they come under dual license. You have the library itself, which is under GPL, command line tools, and utilities examples are under the GPL. So you have two licenses. If you're building code that's under an Apache license, may be perfectly okay for you to dynamically link against the library. It may not be okay for you to use the GPL code. Similarly, if you were doing a GPL license project, you may want to make sure you don't unduly include code that would be proprietary. The other thing is, in a build, talking about packages, there's any kind of funky stuff that takes place. The most funky and the most dangerous is you have code that could be fetched remotely during the build, extracted, compiled, deleted. That happens. You don't know where it's coming from. You have binaries on the one end, unless you actually analyze your binaries, you have no idea to know that somewhere deep in the build, in a third level nested make, you have a W gate that fetched this piece of code, which is under a completely different license. So again, you have lots of packages which have multiple licenses, and you want to know which is the part that you effectively use and depend on, and many other stuff, frankly, stuff that take place during the build. Yeah.
Thank you for the talk. There is another use case, it's related to security, because in fact, if you want to check your binary against some library which may have a flaw, and most of the time in some organizations, the security team is not directly linked to the developer, and it can be useful also to check for, let's say, libSSL, which in a specific version, and you just want to make sure that your binary doesn't include that.
Yeah, that's another. So what I'm focusing here is really the low-level techniques. The prize is, given a bunch of binaries, knowing as accurately as possible what is the corresponding source code. Once you know this exact origin, the applications are licensing, but security is another one. You may have quality issues. You may using, even if it's not a security issue, something which is a pile of bug or some piece of code which is not maintained anymore. All the kind of things that you want to know. You cannot know anything about it until you know what's the package. There's still a bit of work to do after that to understand what's the license, are there any security issues, any bugs, and so on. But you first need to get to know the origin.
Do you know if anyone's used these techniques to evaluate the security or safety of consumer goods that have got embedded systems? So internet-connected coffee maker, to choose an arbitrary device.
So the primary applications, and the reason why I'm doing that is to avoid larceny. No, the primary application and the primary driver has been working with companies that build embedded devices, set-top box phones, where they want to know very precisely, because these are consumer devices which are widely redistributed. They want to comply with the GPL and the licenses, and they're trying to do a good faith effort. They want to make sure they know exactly where the source code came from. And frankly, you have, in all these companies, a lot of churn. People come and go. You have complex stack. You use a lot of open source and free software on the one hand. You acquire software from commercial vendors, and you just mash it all in a big blob. It's humanly impossible over time to know what you are actually building and distributing. So this is the kind of tool that can help, again, for a large device. A better use case in general is you know there's something fishy somewhere, and that's a way really very quickly to hone down on the issue. Am I statically linking the C library in this binary? Yes, no. You can, by running just a build of maybe that single binary, know that in a few seconds. If you build a full stack device, now the interpretation of the whole trace is a bit more involved and engaged, of course.
Okay, that's all the time we have. Merci beaucoup, Philippe.
You're very welcome.